Megan Gallagher, and we're going to be doing a very brief introduction to synthetic aperture radar, or SAR. A little bit of background on it if you've maybe heard the word before, or maybe even less than that if it hasn't come up when you've talked about remote sensing, and then going over some pretty cool use cases and just how we use SAR and ENVI SARscape and ENVI SARscape analytics. So first thing first, what is synthetic aperture radar, or SAR? So SAR is an active imaging system that we can have on satellites or unmanned aerial systems. Some people are even putting it on drones. And how it works is a wave of energy is released from a sensor and interacts with the ground surface. It then has all these bounces that occur from those interactions with the ground surface, and we can get unique chemical and physical characteristics. And so, overall, it's a remote sensing method that we can use to get unique features from the ground. And the reason why it is, well, very much, I wouldn't say up and coming, but becoming so much more popular recently is we have so many more advances in our ability to process large data, because SAR can be very large, increase in resolution, as we're going to be able to see from some laser images, as well as an increase in our ability to get all these different, just when you need it kind of results. So synthetic aperture radar data, along with optical data, have just seen such major increases in the past, even just 2 years, you could say, that we're able to see some fantastic results with these. So first, let's explain how SAR radar signal works. So like I said, you have a wave of energy that is from the satellite sensor or the drone sensor, wherever you decided to put your sensor, and it bounces off the ground surface. And so rough and uneven surfaces, such as rugged areas or vegetation, produce what is known as diffuse backscatter, where the incoming signal is scattered in many different directions, and some of which return back to that SAR antenna. The rougher a surface is, the more energy that is directed back towards the antenna. Diffuse backscatter is sort of a grayscale. In our lovely little grayscale image there, you can see those areas that aren't black and aren't white. That is our diffuse, our vegetation, our rough ground surface backscatter. And so you can see that in that little star scene we have in the bottom right-hand corner. Another kind of backscatter response we commonly see, which is very useful in some of the cases I'll be talking about today, is called specular. And this is off of very smooth surfaces such as calm water or even roads. What happens is the SAR signal hits that flat surface and then just bounces off, and none of the energy returns to the sensor, meaning that it is just black and flat. And the third type is called double bounce. And this is really common in urban areas or anything with urban structures, or even very smooth rock faces. And what this is at first you get that specular response where you're hitting something very flat, but then you hit another flat object, such as the side of a building. And so almost all of the energy is returned to our satellite system. And with that means we get these very bright responses. And so because of this, we're able to get very unique features of things such as vegetation, the ground, ships, water responses, oil spills, just very unique chemical and physical characteristics because of the way our scattering response works. And if that hasn't sold you on why SAR might be something you're interested in, I'm fairly certain this next slide will. So if you're here, maybe you've used optical data in the past, and optical data is usually a passive sensor, or well, it is a passive sensor, which means that we are very dependent on something called the sun for us to be able to get our information. Unfortunately, we have these things called clouds that get in the way of our, beautiful area that we need to image immediately to get the information that we need as soon as possible. And some places on this earth have clouds pretty much every day, and it makes it very difficult to do things such as time series analysis or get information exactly when you need it. SAR, on the other hand, is an active sensor, meaning that it is not reliant upon the energy of the sun. Instead, the energy is in the sensor itself. So we can ignore things like clouds, day and night. If there is smoke or ash in the air, if it's raining, we can actually ignore pretty much all of those effects and still get our information on the ground surface exactly when we need it. And so with that, we can use, SAR and optical together and get all our information combined in one to just make it very easy to get exactly what we need. And if you're concerned, maybe you've seen some old-fashioned SAR images and got a little bit concerned about that resolution, that's not really a problem anymore. So in this lovely image, we have a TerraSAR X image from 2007 that is a 3-meter TerraSAR X image over Indianapolis, Indiana. And we have the same region as seen with optical QuickBird data. And these were both done in 2007. And nowadays we have sub-meter resolution as well to continue to match with our optical data sources. And not only do we have matching, optical data resolution, we also have matching time periods, matching ability to get this kind of data for things such as the new sensors, such as Capella, NovaSAR, ISI, freely available sensors such as Sentinel-1. We're very easily able to start matching that optical data that a lot of people are used to using. And with that background, we can then start going over, all right, so that is SAR, what can I do with it? And the answer is a lot. So some of the most common use cases, if you've ever heard of SAR before, are things such as monitoring earthquakes and volcanic deformation and creating digital elevation maps. These are like sort of the core use cases. We're like, yes, synthetic aperture radar, I can track displacement. But that's not all we can do. They can also do things such as measuring glaciers and permafrost, monitoring and tracking oil spills, looking at long-term subsidence, monitoring shipping for activity monitoring and movement. You can even do things such as biomass studies, deforestation along with that, and flood mapping as just a few of many examples. So there are a lot of different things that you can do with SAR, and pretty much the limits are the limits of your creativity with it, just as you would do with optical data as well. For the rest of this presentation, I'm going to be using ENVI SARscape and ENVI SARscape Analytics to go over some of those, examples that I just showed. So I thought it would be best to go over what exactly ENVI SARscape and ENVI SARscape Analytics are before throwing you into the deep end. So ENVI SARscape allows you to easily process and analyze SAR data. So for things such as creating DEMs or displacement maps, this is the kind of tool you'd like to use. It has built-in workflows and modules to simplify the processing, and it can all be customized. And it has ENVI integration, so everything else we've talked about today can work in tandem with ENVI SARscape. If you want to throw it up in ENVI server, if you have optical data that you're using in tandem with it and you want to use some of the really cool techniques we've seen, and then add in SAR data for an extra layer for classification techniques, you can do that as well. And so ENVI SARscape allows you to go in and mess with every single parameter of pretty much every kind of SAR data available at this point in time to get those output results you need as easily as we can get them to you. ENVI SARscape Analytics is sort of like the grab and go version of ENVI SARscape, where it allows you to perform these very common SAR processing techniques regardless of skill level. So you can easily process and analyze SAR data and generate similar products just like you can in ENVI SARscape. And it also has that integration as well. The difference between ENVI SARscape and ENVI SARscape Analytics is pretty much having to do with ENVI SARscape. I can mess with any parameter I so desire. I can change anything I want to get those perfect results. Whereas ENVI SARscape Analytics is I put in my SAR data of any kind, because it's data agnostic for SAR at least, and I hit go, and then I'll get my output result. So I don't need to worry as much about the different kind of background parameters, and I can just have it run and get what I need from it. So for what we'll be seeing for the rest of the day, these will be what we're talking about. The first example that we're going to be really getting into a little bit of detail with is automatic ship detection. And this is why I thought it was a pretty good idea to define those radar backscatter responses in the very beginning. Because with SAR, it is easy to find where ships are or where they're saying they are and they actually aren't. And this is because of that backscatter response. Water, as we can see in this lovely scene here, is very black. It is very dark. And ships, because they are urban structures and they're just hanging out on top of that water, they have these little very bright spots that are definitely, very different from the water themselves. So things such as automatic ship detection are very easy to use in synthetic aperture radar responses. And so in SARscape and in SARscape Analytics, there are very specific tasks and workflows just exactly for this. You put in your SAR scene. If you have AIS data, which we'll get into in the next slide, you can have that as well. You get a land mask, so you ignore the land because there hopefully aren't ships you're looking for on land, though you can do some pretty fun things with that. And then you hit go. With that, it'll be able to pick up where the ships are and, well, sometimes where the ships aren't. So in addition to simply detecting ships in a SAR scene, you can also use AIS, or automatic identification systems, data to compare your results. AIS beacons are required to be transmitting on large ships at all times. However, sometimes ships turn these signals off or alter them to report a different location. The combination of SAR ship detection and AIS tracking through the SAR AIS classification tool can identify which ships were identified in both the SAR scene and in your AIS data, and which ships were detected in a SAR scene and maybe not in the AIS data, indicating, something had occurred there. And here we have a lovely little example of, where ships have been detected, where AIS were found, if there are matches, and if there are not. And so very easily in both of the SARscape and SARscape Analytics, we're able to just pick out, that's an interesting little feature right there, have it classified, have it ready, and put it where you need it to be. A more recent example of this was done by a member of our L3 Harris team. And this should look unfortunately familiar to everyone if you've been keeping up with the news in the past month. And this was an automatic ship detection of all the ships backed up on the 25th of March by the Ever Given blockage that occurred. And so with this, there's an automatic counting tool. So 151 ships were detected having been stuck and unable to go through the canal here, which is a lovely example, but also just ouch. So with that, the next little example we're going to be talking about is a bunch of tag words all put together called coherence change detection. So coherence change detection uses both the real and imaginary portions of the SAR wave and uses those to give us not only that grayscale intensity response change, but also minor changes to the physical surface that we're able to get from things such as the phase. And with that phase information, we're able to pick up things that you can't get with pretty much any other system out there. And I will be much more better to show that in the next coming slides with the examples we have. But I wanted to talk through first how this situation works. So this is an example of a normal SARscape process where you have this little workflow that takes you through step by step. The first thing you would do is input your data, input your area of interest, and have a DEM ready to go. And then you'd go to the next step, which would do just some making sure everything is where it should be. You can cut down your data if it's very large there as well. And then you just hit next to go to the next step. And that's where it starts comparing your scenes to each other. And so for this coherence change detection, it is a change detection over time. And so it'll look at your scenes, see how much has changed in between them, and start doing some background analysis and processes on those changes. Then it'll take your SAR scene and geocode it. So SAR is a non-nadir looking system, meaning that it doesn't look down like normal optical data. Instead, it looks to the side. Because of this, sometimes when you collect the SAR scenes, they can be upside down and backwards. And so we need to make sure that they are where they should be on the Earth's surface. And that's the geocoding step. And lastly, we can generate output results that give us information on the scenes themselves. And this is one example of a SAR CCD, or coherence change detection. So on the left-hand side of this image, or the left-hand side of the screen, we have an optical image, which is around Green Village in Syria, where we're seeing a lot of sand and some roads. On the right-hand side, we have our SAR CCD response, which is showing something very different. And so in this one, we have this oil facility near Green Village, which with the SAR CCD, we're able to see a lot of tire tracks, which are not on the roads, and in fact are just imprints on the sand that we can't see with optical data, and that we can barely see with any other kind of system, but we can very easily pick out with this SAR coherence change detection. And so with this one, we're able to pick those out. And in this case, it was these purple lines, the right-hand image, are tire tracks that are pretty much stealing oil from this refinery and selling it to neighboring villages to pay for, in this case, it was terroristic activities. And so with the SAR system, we can just pick those out and immediately see them. Another example, and my favorite example, which we'll see a little bit more in depth in a couple seconds, is Burning Man. So this is coherence change detection over the Burning Man festival here in the United States of America, where we're able to see the change from before, this was all desert, to the creation of all the artwork and structures and tents, and even once again, the imprints of tire tracks in the ground of the cars creating their own roads to get here. And so with that, we have a quick little video too of how SARscape Analytics is able to use change detection. And in this case, I'm running it in ArcGIS. So I opened up our toolbox here, and I'm just using my 2 Sentinel-1 images that I used for this. So this was from before and during the Burning Man. I'm choosing a small area of interest, so my processing time is shorter. And then I have a DEM already in there. I choose an output folder, and then I just hit OK once that's set. Through the magic of editing, this is already complete, and we're able to see some of our change detection that is occurring on the surface. Here we have a filtered classification map of change detection and an unfiltered one, and this is just stuff you could have on during the processing in SARscape Analytics themselves, as well as you can look at the background processing of the SAR scenes and see how these changes have occurred there. And so you're able to see things such as significant changes, where things have been built, where things have been torn down, and even things such as humidity changes in our scene. So very easy to run. You just throw in your data and you hit go. And the last major thing I'm going to be talking about today is using SAR to track movement. And this is for long-term time series analysis of changes. So things like subsidence in urban areas, and especially dams recently is what I've been doing a lot of work in. And so the 2 methods that we talk about when we do this kind of thing are persistent scatterers, which is known as PS, or small baseline subsets, which is known as SBAS. PS can be used in cases that are showcasing linear behavior, and so this is like urban or non-urban areas, such as outcrops that have these things called persistent reflectors, or where we get very bright responses constantly. So PS is really the best to be used in urban cases. And SBAS can be used with nonlinear behavior. So this can be modeled as quadratic or cubic, and can be used in those areas where there might be a lot of, well, not a lot of vegetation, but where there might be vegetation, or they might be just a bit more, not as urban areas for us to get information on. So an example of this is the Highway 36 collapse that happened July 12th, 2019, near where our office is in Broomfield, Colorado. A large crack began and all the eastbound lanes were closed because pretty much the entire east side of the highway collapsed. And so I thought it'd be interesting to see if we could have noticed this collapse far before it actually happened. And so I won't get too much into the details here, but I figured you guys might like this slide, where we have what kind of processing was done. And this is using the technique called SBAS. And at the bottom, we actually have all the SBAS tasks lined up as if I was putting them in the modeler. So first, what you do is you see how interconnected all of your scenes are. For running this kind of process, you want usually 30 SAR scenes over an area. Then, so once you see how connected they are, you what is called generate interferograms. So you look at the similarities between each scene. Then you refine them and you try to get that movement that has occurred in between them. And you go through 2 different inversion steps. And those help you find the modeling and completely remove atmospheric effects, which is a scary thing to say if you've worked with any kind of optical data, but I can actually say here. And lastly, once again, we make sure that it's no longer upside down and backwards. So, with that there, and if there are questions about that afterwards, I'd love to get more into the processing, but I wanted to show you the pretty pictures more so. We can look at the changes that are occurring around the surface of Highway 36. So here we have vertical displacement, where these areas on green and red and blue are shown, and their changes on the surface. So Highway 36 is where that little white arrow is, right in the middle is where the collapse occurred. And we can track and see that one is actually that lime green line on our chart where suddenly around the end of, I think it was May, we see a drastic response downward. And so May to July, that's about 2 months of change. That's pretty good if we were able to track that and map it beforehand. But we'll also see some other areas of major movement here as well. And we also have a stable point, for example, for comparison. But when it really comes into play is when we're actually tracking that vertical and horizontal movement. So with SAR over time, you can track vertical and horizontal change. And so our vertical change, once again, we can see at the end of May, there is a massive shift of this part of the highway just moving downward. But when we're tracking horizontal movement, it's not fantastic because it has been shifting for the past year or even more. And this is why we like to have a lot of SAR data so we can extend that timeline and see when this change occurred. However, in this case, what was interesting is this part of the highway was built over a dried up lake bed. And it was found out afterwards that not everything was done completely as it should be for the compacting clay that we have in Colorado. And so when we're watching that horizontal displacement over time, and if I build up a longer baseline, we could be tracking the very slow horizontal change as that highway began to sink into that dried up lake bed. And I have a couple other examples here of just, once again, dam monitoring is a very common ask we have here of just looking at and seeing these kind of changes that are happening on the surface. So these examples are using persistent scatterers instead. And here we can track vertical changes over time, which are mildly horrifying to see, to be honest, all on the surface of dams and as well as surrounding mine areas. So we can click on these, and in PS, you can see we get little shapefile points that if you click on, you can see how these things have completely changed over time on a graph. So first we have Miramar Azul here, and we can track and see some major changes that are occurring on the dam face. We have a couple more examples here. This one isn't quite as bad, luckily for us. This one is one of my least favorites because I am absolutely not very happy with the fact that we have both increase and decrease along the same plane of this mine. But this is also a really great example to show one other thing when we're working with persistent scatterers. And that is in the top right-hand side of the scene, we have this huge area, which is showing red, which is showing major movement. But that is actually water. And so when we're working with SAR and when you're working with any kind of remote sensing system, you always need to be aware of what you're looking at. And so for that case, that red on that lake bed is just the changing of the water levels over time. And so, if I was focusing on these dam studies, like I do quite a lot, or if I'm looking at any kind of areas of movement, you just need to be aware of, are they mining there? Is the movement there normal because they've decided to do construction? That kind of stuff as well. So here, these are just a few of those examples of, pulling out these kind of features from synthetic aperture radar. And hopefully I have piqued your interest a little bit on all the different things you can do with it.